Welcome to Dream Seminar 6. This is an interesting one. Well, they're all interesting, but this is so it's called Understanding the Behaviour of the Mathematical Community. I deliberately didn't write Behaviour of Mathematicians because I'm not trying to talk about us as individuals today. I'm trying to talk about us as a community and what that means for us as individuals. So the focus here is what we do as a blob. And then what the blob does influences all the points of the blob. So, in order to save time, I won't run through the actual sort of social experiment. But if you recall the introductory lecture, when I spoke about the oil pipe problem, for those who weren't here, the problem was as follows. I have an oil rig out in the ocean, I have an oil refinery on the shore, and I've got land here, and the sea is here, and the question is, what's the optimal path for a pipe from the rig to the refinery? And I've got the cost is something like alpha dollars per kilometre in the sea, and beta per kilometre on land. I've run this with students, some of whom are in the room actually at the moment. So I ran this. I stuck this problem on the board, and I said, compute this, and I even said, this is the distance from the refinery to the perpendicular here. This is here. So I put the problem up. Did this first time in 2016. Put the problem up. 3 blackboards, not 3. 3 students came up, started solving it. One said, oh, well, where's this distance here? I said, oh, well, yeah, good point. We put a distance there, sorry. And then they said, okay, cool. And they went along and solved it. They computed the optimal path of the pipe from the rig to the refinery. What did they all do? They did some calculus, one did some trigonometry, and they basically got this. I did this in May 2016. I did this in October 2016. I did this in October 2017. Same result each time. 9 different students, 9 different year levels. It's never failed me. Everyone goes, great, yep. Oops, need to ask this distance here. Now I've got that, the problem is perfect. Some would say, is alpha bigger than beta, or is beta bigger than alpha? That was about the extent of the depth of questioning that happened during the little sort of problem solving. So I introduced this as, let's watch people do mathematics. And see what happens when people are actually doing mathematics in front of our eyes. Because maybe you haven't seen mathematicians doing, unless you do. Unless you can do your example sheets in front of a mirror, you probably don't actually watch the mathematician solve a problem. So I did this. And eventually, after a while, I said to the students, what have you solved? And they said, we found the optimal pipe. And I said, really? What do you optimal? I said, well, it's the minimum cost pipe. I said, that's great. Whoever told you optimal is minimum cost? And they said, but of course optimal is minimum cost. Really? What happens if there's something here? What happens if there's a coral reef here? What happens if there's some sort of, critical blood centrifuge system here or something? Boom, no more blood transfusion in the UK, but hey, you found the optimal pipe. But my point is that, every time I've done this, 9 different students across 3 different year levels, always the same. We ask for the distance, we ask for no other questions. No other what's going on here. Now I've had to think hard about why this is the case. Actually, this is not to be unexpected at all. Because we train you to solve mathematical problems like this in a purely mathematical way. We train you that optimizing is over time and money, basically nothing else. What do we train you? Well, we put you through 500 example sheet questions a year. You ever counted them? 500. If 4 years, 2,000. 2,000 example sheet questions. Each one takes you what? 20 minutes on average, maybe half an hour, 2.5 hours, a week. bit it up here. Right, so we put you through thousands and thousands of hours of training in the same style, the same way. Oh, what's the refined math problem? Oh, what's the refined math problem? Every single time. And after 4 years, you've learned how to do that. And so in the process of beating the mathematics into you, we've beaten everything else out of you. After 3 or 4 years of doing this. So it's no wonder that when I give a problem like this to 3 randomly chosen mathematicians, even ones who are in a lecture called Ethics in Mathematics. And one of them was the president of the society at one point, that was quite funny. Still fell for it. Even in a lecture in Ethics in Mathematics, we click into math mode. And go, oh, well, math problem. 0, 1, 1, 1, 0, 0, 0, 1. We detach. Because that's our training. It's a training that we give you. Right? It's a training that we've designed, we've engineered it, and then we serve it to you. Several times a week for 4 years of your life. And that's the outcome. So I'm trying to understand what it is about that. I'm trying to sort of tell you what it is about that. So the things which make us good at mathematics, the qualities, the skills, the understanding, it's the following. Firstly, I'll write these up. Precision. I can do something exactly, I won't make a mistake, I won't mess things up, I won't drop something. Focus. I can concentrate on this without other things cluttering my mind. The ability to filter information. Pick out the bits that we want and ignore the rest. Here, I don't care what colour the sand is. It's not going to affect my calculation. I don't care if it's Monday or Tuesday, the cost should be the same. I filter out, I need this, missing this. What else am I missing? We can filter down to what we think we need. And the ability to go deep into thought or into problem. Okay, these is what we train you to do. This is what we look for when we admit you, this is what we train you to do, this is what we hope we can do at the end. There's a lot of work into this. To make sure that this is what you come out with. But what does that mean? What's precision? Precision. No breadth or no room to move. Be precise. It must be exactly 4.2 meters. You don't give yourself the opportunity to say, well, actually, maybe we don't want something to be totally precise like that. Focused, undisturbed thought. Rigid thinking. I will think like this. This is how I will look at it and phrase the problem. The ability to filter information out. That's good. It's also bad, because what happens? You can block important factors. Deliberately block them out. I don't care what's here. Don't want to ask that. It's not important, not relevant. And the ability to go extremely deep into thought and into a problem. From that perspective. All the things which make us good at mathematics are exactly the things which make us terrible at using mathematics. Nice little one-to-one bijection here. And the fact that you laugh at that is an indication that we have a community. And I can start using terms and norms and phrasing from mathematics, and I can drop it into an everyday conversation. Okay, I can't do that. I've got an audience of art historians. You know, I've got a great projection between Rembrandts and Van Goghs. Okay, they'll stare at me blankly. I can do that with you. Because all of a sudden, the mathematics that we train you on the page seeps out. Our greatest strengths are simultaneously our greatest weaknesses. And we don't tell you that. These are the things which make us easily manipulable, they make us blind to society around us, and make us produce results and analysis that is totally out of context with the world. Autopilot problem. I've done this so many times now. I'm totally convinced. I'm going up to Newcastle on Thursday. I'm going to do this again. And it's going to work. It always has. Unfortunately. I wish it wouldn't. I wish I was wrong. I wish I could get in front of a room full of mathematicians, maybe some Komskis, put this up, and they'll go, well, obviously, what about this, what about this, what about this? They'll start asking questions I don't even know think to ask. Oh, yeah, shit. No. That would be great. Good problem to have. Haven't had that problem yet. And I doubt I'm going to get it anytime soon. Because of the 2,000 questions that we throw at you to train this into you. That's why I'm not going to get it anytime soon. Unfortunately. We have no moral code of conduct. We have technical understanding, but no way to operate morally that exists in our community. And I thought about this for a while. I tried to think, well, where else have we maybe perhaps seen this in society? And the one example that came to mind, and it's an old example, old with a capital O. If you think to the training of the longbow archers under Henry V. Okay, this is sometime in the 15th century. Basically what happens, Henry set up a little sort of reward system. He realized, archery, it's the way forward. Let's do this. So every town and village in England was told, because at that point England owned Scotland and a little bit, so just England was told, okay, we have archery contests, and if your son can shoot well, they'll win a few silver pieces. And if they win, then they can go on to the district championship, and there they can win some gold pieces. And if they then win the national championship, they might even win some more gold pieces in the gold cup or something like this. So all of a sudden, every kid from the age of 5 is shooting bow. Every day. Boom. And they're trained to do this for 10 years. When you shoot bow for 10 years, your perception of stuff changes. You stop looking at the bow and the arrow when you're shooting. You only look at the target. It's how you shoot. And you train these people for 10 to 15 years, every day, hours, shooting bow. It's actually done in a lot of solitude. You don't do that. Apart from meeting people in competitions, not too similar to Olympiads, you do this by yourself. Okay, so actually these people came in quite useful at Agincourt. Henry got them all together and said, great, we're going to have a longbow army. Actually, he got archers together. They trained in general archery. And then you can sort of get people up to speed in longbow. It takes a few more months because of that 15 years pre-training. Okay, so you've got this awesome longbow army. Really, really good at shooting bow. Dead accurate. Great. The French start marching, it's a bit muddy, they sort of slow down a bit, sitting ducks. Boom, boom, boom. Okay. You get the upper hand at Agincourt. Now you have a whole bunch of French prisoners. And now the king says, right, There's kind of too many prisoners. Let's start slitting some throats. This is a bit inconvenient. So archers aren't your only people in the army. You've got knights as well. And the knights said, no, we don't roll like that, sorry. We don't slit throats. That's not part of the code of chivalry. Because knights were also trained in a certain art of fighting, but they had a code associated to that, code of chivalry. You capture prisoners. You sell them back and get some ransom. That's how we roll. The archers, they were the new kids on the block. Great new technological understanding, a lot of focused training, no code of conduct. So for them, when the king said, right, start slitting throats, they're like, yeah, okay. Completely different. That's what happens when you have a technologically powerful group that haven't thought about what their actual action technology are doing. You train people in a sort of intense, focused way for years. So for every example sheet question you've done, they've shot 1,000 bows. Very good at that. Very focused. Very strong. Doing archery changes the shape of your body. Talk to anyone. One of my summer students this year, he'd been doing archery for 1.5 years, and already he's getting a bit sort of shoulder heavy on one side. Do it for 15 years, you're going to look like that, which is really handy for shooting bow. What happens to your brain when you do this for 15 years? When you do thousands of example sheet questions? What does it do to the way you see the world? Same repetitive motion again and again, the same distillation of problems, the same reductionism, down to pure mathematics. Get rid of the colour of the sand, I don't care. Who cares how many fish are swimming around here? Might be fine on the training ground, might be fine in your exams. Then you go outside. You leave. With hypermobility, you leave academia. You do something else. This exact set of skills which we trained into you, somebody now has to try and train out of you. So how does this happen? How do we get to this point? Training you in this particular way. What is that mathematical training? You got to think the way that we teach mathematics, the way that we design courses. We design and teach mathematics courses for the 10% of students who are going to follow in our footsteps. And I've heard this said to me verbatim from different academics, different institutions, top institutions, Cambridge, Heidelberg. Different academics, different institutions, different backgrounds, different nationalities. We design and teach mathematics for the 10% of students who will or might come to replace us. For everyone else, they can come for the ride. We'll happily, we can lecture to 25, like we can lecture to 50. You're welcome to join us. But that's not who we're training. That's not who we're designing things for. We're designing setting up the entire system for the 10% who might come along to replace us. And actually, it's less than 10% who do replace us, but approximately 10%. The 10% we think might come to replace us. The rest, just fodder. I mean, you're good at math, sure, but it's not that other 90% that the system is designed for. And they will say that. Ask top-level mathematicians how courses are designed, who they're teaching for. Maybe don't do it here. Go to another university and ask around there. Or ask people who can talk to their PhD supervisors somewhere else. If you want to sort of maybe anonymize yourself a bit.